Good morning, everybody. Welcome to my presentation of the ion channel project. I did this project for my Springboard second capstone project, and we followed all the steps of a typical data science project. We first defined the problem, did some exploration, created some features, designed machine learning models, and then drew some conclusions. Let's dive in. The Ion Channel project was a Kaggle competition that was organized in the spring of 2020. Ion channels are present at the surface of cells, and as you can see here, so they're in the membrane, and they can be either closed or open. When open, they let ions in and out. It's very important in physiology because cells behave differently when they have their channels open or closed. And you can even find that cells have a problem, some diseases, if the ion channels don't work as expected. Scientists have been looking into these ion channels for a long time. And how do you know if a channel is open or closed? They use an electric signal that's measured at the surface of the cell. I won't go into details, but basically you measure this current here, and a trained scientist can tell, based on the current, how many channels are open and how many are, or if it's open or closed in this case, between 0 and 1 open channels. The goal of the competition was to take this signal and predict the number of open channels to replace eventually the manual process of having to convert this signal into a number of open channels. So as I said, we would use a signal, and the host of the competition have provided two sets of signal, the train set here on top, and then the test set. And they explained that each, so it's 5 million data points for the train set, and they explained that it consists of 10 separate experiments of 50 seconds. So each of these color-coded portions of the signal represent one batch or one experiment. They were taken maybe on a different day or in different conditions. They're just different experiments. So 50 seconds, and each of these is 500,000 points. So the acquisition rate would be 10 kilohertz. The test set also has kind of the same division into different experiments. One thing that really stands out is these baseline here are not really consistent. So the competition hosts have warned us that there was a drift that had been synthetically added to the signal. So they added that to add some complexity to that problem. The first step will be some signal processing to remove the drift and maybe some noise. What we also see is that signals can be probably grouped based on the intensity. Like here, the amplitude of this purple signal is much larger than, for example, the green or the blue portion of the signal here. And then we're going to take a look at the distribution of the open channels to see how it works, like if they open and close fast or slowly, how long they remain open, and things like that. Signal processing was not my strong suit, and the beauty of this Kaggle competition is that a lot of other competitors have shared their notebooks early on, and so people with a lot of experience could explain concepts that I was not familiar with. The drift was removed, for example, by Chris Deot, and what he found was that there was a sine function that had been applied to batch 7 through 10, and even batch 2 actually had the same sine function, just stopped after the first few time steps. So he removed the drift, and this is the signal after the drift has been removed. I did not need to reinvent the wheel. I took his work, and I thank him, by the way. The other thing that we could do to improve the signal was to remove some noise, and that's typically done by applying a Kalman filter. We tried to use our own Kalman filter and set the parameters ourselves, but the results were terrible, and we ended up downloading the signal processed by Michal N. And here's an example of like a small section of the signal. You see in blue the original signal, and then the overlay in orange is with the Kalman filter, and you see that it removes a little bit of noise, but not too much. Essentially, the signal is still there. So from now on, we are going to look mostly at the train signal, and I overlaid in orange the number of open channels. And you see that, obviously we cannot do that on the test set since we don't have the label. That's why we only do it for the train set. We see that we have between 0 and 10 open channels, and we already suspected that we had groups of signals. Let's look more closely. So it seems like batch 1 and 2 have kind of the same look, and if you zoom in, we see that it's either 0 or 1 open channels, and it switches between the two, and the signal sort of follows the opening and closing of the channel. Batch 3 was different, but it looked really similar to batch 7, so we put them together. We are going to group them together, and same thing, it's between 0 and 1 open channels, except when we look closely, this batch 3 and 7 had a much faster rate of opening and closing, so this is more representative of the batch. So we called it 1F because fast. We could group batch 4 and batch 8 since they had similar properties too. And we have between 0 and 3 open channels. As you can see, it like really goes up and down, and the signal again follows relatively closely. We notice also some noise in signal in batch 8 here. 5 can be grouped with 10, and we have between 0 and 10 open channels, and as you can see, this is a little bit more complex because it changes a lot between 0 and 10. And then 6 and 9 will group together, and these have between 0 and 5 open channels, so we called it type 5. 1 slow, 1 fast, 3, 5, and 10. And as you can see, 5 and 10 are really more complex than the rest. Knowing that, we wanted to look at like how fast or slowly channels open and close, and so we looked at the number of time steps in each state. This is just an example to remind us how it looks. And we could see that it spends most of the time steps with 0 open channels. 25% of the time, almost, there are no open channels. And then that goes down as the number of open channels increase, with 10 open channels being the lowest configuration, with less than 1% of the time. But that didn't really tell us, if it was opening for a long time or opening and closing quickly. So we tried to look at the number of intervals, and I highlighted them in blue here. So instead of counting how many time steps we spend in each configuration, we count the number of intervals. That would be 1, 2, 3, 4, 5, 6, 7 for this portion of the signal. So no matter how long they last, if it's just for one time step or for more, we count them as one interval. And when we did that, we got a very different histogram. We can see that we have only a few intervals that have 0 open channels, and it's 3 open channels that has the highest number of intervals. That also means that if we spend a lot of time in 0 but very few intervals, we must have longer intervals in configuration 0. To kind of understand that distribution, we did a box plot, and as expected, we have a lot of outliers here for the length of the intervals in each state. So in state 0, 0 open channels, we have a few very, very long intervals that drive up the number of time steps in that configuration. It's very hard to see here at the bottom, so I zoomed in for you. And you see that the median for the first 5 configurations is 2, and then 1 for all the others. So it's usually very, very short intervals that we see, and then outliers, especially for 0 and 1. That's good to know that it's oftentimes fast changes. Okay, so now that we know all this, what are we going to do? We want to design a model to predict the number of open channels, and we can either work with a regression approach, because we're trying to predict a number between 0 and 10, or a classification, which would have 11 classes. We will try both. The metric for this problem is going to be the macro F1 score, and that's just defined by the competition hosts. So the F1 score is a classification score, and for a multi-class problem, you have one F1 score per class. We can do an average, and the macro one means that the average is unweighted. That means that for class 10 open channels, which has only 1% of data that are in that configuration, a mistake would have way more weight than in configuration 0, for example, which happens 25% of the time. So that's good to know. Mistakes in the higher number of open channels will cost us a lot in terms of score. We tried very basic approaches, but the focus will be on ensemble methods, boosting on decision trees, and then neural nets, more specifically CNN, convolutional neural nets, because it's a time series, so it's suitable for this problem. All right, we only have the signal as a feature, and we think that for decision trees we will need a little bit more. So we decided to create a few features, and we started by doing a few rolling statistics, and we randomly picked 5 windows. We have centered windows and then right windows. So for time step X here, we generated features with a centered window like the red one, and with a right window. It's actually to the left of X, like the blue one. These statistics were the average, here it's in black, the minimum, maximum, standard deviation. We took the kurtosis and the skew edge too. And as you can see, it's different for the centered and right window. The max is different, minimum, and even average. They're all different. And we thought this is important to kind of look at what came before as a way to predict what's happening at time X. We also created a few features that were operations on these statistics. For example, the max to min ratio, the difference between minimum and maximum divided by the average, that kind of thing. We then generated features that were analytic functions, the power, the square root. We tried the exponential function, and the likes. And then we had a few lags, so that's a time point before. We did the -1, -3, -5. We thought it was important to know what came, shortly before. And then we took also the 2 that were coming after. Down the road, we found out that we could use the integral, derivative, and then a function, a feature that we call peak detected. I'm going to go over these 3 really quickly. The integral is, for a signal, just the cumulative sum of everything that comes before. What we did here is we took the integral over the previous 10 time points. So in blue you have the signal, orange the number of open channels, and the green trace is this integral over the past 10 time points. And 10 was determined arbitrarily. We just took the one that looked best. It looks a little bit like a very smooth version of the signal, and we thought the model could learn from that. It looks really similar for batch 1, so type 1, but then when we move to the types that are more complex, it still follows the signal closely, but it's not as like following as closely. Of course, it's a smoothing type of function. But still, we used it, and we thought maybe the model can learn something from it. The derivative was interesting because, as you can see here, so same as before, signal in blue, number of open channels in orange, and then the derivative is in green. Every time a channel opens, or every time there is a peak here, there is a peak in derivative, and every time it dips, you have a dip but below 0 for the derivative. And we thought that could be helpful also for the model to learn when it opens and closes. We just feed it to the model and see what happens. Finally, peak detected is a bool that we created based on, from the find peak function of SciPy. This function takes a lot of parameters, of arguments to kind of fine tune, but then it finds peaks in a signal. And this is an example. In orange, we point at the places of the signals where a peak has been detected. And we tried to tweak the parameters so that it would detect all the peaks that were actually an open channel, even if we had a lot of noise. And we hope that the algorithm could do something from it. So altogether we had 139 features, and we'll see what happens. All right, machine learning. We started with regression, treating it as a regression problem, and we had terrible scores. So we quickly switched to a classification. We had a total of 96 submissions for this competition, and don't worry, I won't detail them all, but I'll go over the most relevant ones. For those who have never participated in a Kaggle competition, I want to explain what's a public and private score. So the competition hosts provide the train set and the test set. The competitors submit predictions on the test set, and they receive a score. For the entire length of the time of the competition, the score is a public score. So it's only a portion of the test set that is used for this score. In my case, it was 70%. So it gives us a good idea on how our model performs, but it's not the whole test set, so there is a small chance that we're overfitting on that portion of the test set. So they keep the last 30% a secret until the end of the competition, when they release the private scores. And that's just to keep it interesting, I guess. And we don't really know, like, the day the competition ends, it happens that there's just a shake-up of the leaderboard because some models generalize better than others. So when you see down the road public and private scores, now you know what that refers to. I said we would use two types of methods, and that's ensemble methods and then neural nets. Let's start with the decision trees. We used CatBoost and XGBoost, but mostly CatBoost, to try to predict the number of open channels. And this is an overview of all the submissions that we did for CatBoost and XGBoost here. As I said, I won't detail them all. I just want to go over a few important things. So first off, we started with scores that were already quite good. This is all the public leaderboard. We started at 0.8, which really wasn't bad. And then we were able to improve to 0.938 rather quickly. We had some hiccups down the road, but then from there we kind of stalled and we weren't able to get much higher than that. So 0.94, is the highest score we obtained on the public leaderboard. So that's important to know. All the improvements, the small things here, didn't really lead to big changes in the score. And then I'll just go over the main changes. So between this first block and the next one, what we did was use wider windows for the rolling statistics, and that helped a lot. We used in the 1,000 rather than the 100, and that helped a lot. The next time it went up was when we, or it improved, was when we used the derivative and then the lag of the derivative. That was really good. Here we added peak detected, that bool feature that I was telling you about. That helped too. We think it improved when we added the integration on the previous 10 time steps. And then we generated the features per batch. And the reason is that you remember that all the experiments are one after the other, so the rolling windows, the windows can actually overlap between different batches, and we thought that would lead to errors. So we generated them per batch rather than like on the whole train set at once. And then we noticed that our model, this is the accuracy, had good accuracy for the lower numbers of open channels, but was performing very poorly for the higher numbers. And that's kind of what we expected, since after 5 open channels, it's really a faster rate and changes that are hard to notice in the signal. So what we did is that we created a separate model only on the batches that had 5 open channels that were type 5 and 10. And then we used that model to predict the number of open channels on the entire set, and we called that high cat boost predictions, and we used it as a feature in our next cat boost model. And that went well. I mean, it didn't improve the score that much, but we thought it was an improvement. And then finally, we improved the square root, the way it was calculated. Since a lot of times the signal is negative, we wanted to have to avoid having any values throughout the data set. And so we just remove the sign, take the square root of the absolute value of the signal, and then reinsert the sign. And that was, not too bad. When we got the final results, the private score, this is what happened. So small changes. What I forgot to tell you is that you can submit as many models as you want, but for the final submission you have to pick 2. And so we decided we had a lot of models that were 0.94, and we decided to go with the very last one with all the improvements. We thought it was our strongest model. Turns out we had a better model before, one that was just after adding the peak detected feature, but before generating features per batch, adding high cat pred and all that. So we had a better model that had a score of 0.9387, which was slightly above 0.9372. We didn't know. All right, the second type of models was neural nets. And again, this is a lot of submissions. Really quickly, we tried a bunch of different architectures. We used TensorFlow and Keras to do a fully connected model. That one was with all the features. It didn't go too well. We did 1D CNN. Since it's a time series, we thought it would be the best architecture, and that wasn't great. But then we switched to a WaveNet. And the WaveNet is an improved version of the CNN. So it was developed for audio files, and what's important is this dilation. concept that makes it that one output node takes input from not 5 but a lot more inputs here thanks to this dilation. So it's a way to look at more time steps without adding a lot of complexity to the model. In short, the features that we used were that at first we started off with only the signal, and then we took the 3 or 4 most important features that we found that they were important thanks to cat boost. That has a feature importance parameter. And then we also used the cat boost predictions multiple times, and those were actually the best models. So we were able to reach 0.94, but only when using cat boost prediction. So at that point, how different is it from using cat boost directly, really? So here we used cat boost prediction again, cat boost prediction. So for all of our top performing models, we used cat boost. So we didn't really know which one to pick for final submission, and we decided to take an average of our 2 best WaveNet models and then 3 cat boost models. And this is what we ended up submitting as our second submission. As you can see, it scored well on the private leaderboard as well. So that's all of our models. As I said, we kept one cat boost model for the final submission, and then the average of 5 models for the second one. And without further ado, the results. So the winners scored 0.9851, but they found a small leak in the data. So that means that, as I said, some of the data was generated synthetically, and they reverse engineered it, and they found how the hosts had generated some of the signal, which gave them a clear edge. So I want to give you the score of the top ranking team who used only machine learning, and that was the third team, and they scored 0.9582, just to give you an idea. My best submission was the average model with 0.9379, so I'm actually not very far from these guys. However, I'm over 1,000 spots behind them in the ranking. I was still able to perform in the top 47%, which was really good, in my opinion, for a first competition and the first time using neural nets. My best model, I told you one model performed better, even though I had not selected it for final submission. And that was one of the earlier cat boost models. With that one, I would have ranked a little, like 100 places higher than what I did. And that would have been in the top 43%. Overall, I'm very happy with my participation. It was a lot of fun. I learned a lot. I think the approach with a lot of people, experienced Kagglers, sharing a lot of their notebooks and their knowledge in the beginning was very good for me. I learned so much about signal processing, and even the WaveNet and all that were inspired by other people. And overall, I'm very pleased. I want to thank you for listening to me. Thank the other Kagglers. I mentioned Chris Deot and Michal, who shared their notebooks and their data sets. And then I want to thank Diraj, my mentor, who helped me when I was frantically submitting. Thank you all.